It's interesting, in grade 10, you talk about, you do a lesson on, or you do a unit, sorry, on factoring, and you learn how to factor, you learn all these skills, and you maybe learn some other algebraic skills and practice some other stuff in there. You do that, and then you do a unit of solving quadratic equations. So it's very much the same in this course where we just spent a unit. We talked about a bit of graphing and other stuff like that as well, and we did some other things, and in fact, it's kind of the same in grade 10, but we did all of that. And it was all like functions. It was all equations of functions and graphs and that kind of stuff, everything we're doing. So you were just factoring. And then in grade 10 and also here, then very next unit, we're solving. So that's what today is all about. Now the difference is in this course, we only spend 1 day solving this type. And then we're going to do solving other types of things. Some of them are equations. Some of them are inequalities. Okay, there are similarities. One of the hard things about this unit is all of the different things that we're going to solve, different kinds of equations and different kinds of inequalities, have different procedures, obviously, to do that. But there's similarities. So a big part of what you are trying to figure out over the next 2 weeks is, when do I use which technique, and when do I need to do this versus when do I need to do that, and all that kind of thing. I hope that makes sense. It'll obviously make more sense once we've done everything, but that's a big part of this unit, is separating the different procedures for the different kinds of equations and inequalities. We're only doing solving polynomial equations for 1 day, but we'll be working with polynomials for a few days after that. So all the factoring we've been doing, we're going to do for a few more days. And so it's kind of similar to grade 10 like that. And in grade 10, you do this thing called the zero product property. And the zero product property states that if you have two things that multiply to 0, then either one of them must be 0 or the other must be 0, or I suppose both. And I would challenge you to find two other numbers that multiply to 0. Like what? -5 and 5 multiply to 0? Of course not. It's -25. They add to 0. But if two things, numbers or whatever, are multiplying to 0, one of those things has to be 0. And then you can extend this, because in grade 10, we're only dealing with quadratics. That would only be two things. And then we extend this property to not just two things, but any number of things. So if it's degree 3, it might be 3 things, or in this case, it looks like it might be degree 4 because it's 4 things, because it's A times B times C times D. Then one of those following must be true: A equals 0, B equals 0, C equals 0, or D equals 0. And that's the simple part of what we're doing today. In the last unit, as I said, we were factoring. When you're solving, there's one extra little step, but it's pretty easy. But there are a few different cases that we're just going to make a note of as we work through the material, the examples today. That's kind of what we're doing. Does that make sense? Any questions on any of that? Do you remember talking about the discriminant? Did we talk about it in this course? I think we probably did, didn't we? But some of you may have seen this in grade 10 or grade 11, and some of you would not have. And I think it's really useful, and I would strongly encourage you to use it whenever you can. And after we've seen a couple of examples of using it, it makes a little bit more sense in exactly how it works. But essentially, it tells us about the nature of the roots of a quadratic. Not only does it do that, it'll give us some insight into the best, most efficient way of solving just the quadratic part. Again, we're dealing with higher degree polynomials. But for the quadratic part that we will end up with at the end, this will give us some insight into how to solve it. When you solved quadratic equations in grade 10, how many different kinds of answers might you have had? You could have 2 or 1 or none. Right? When you had quadratics, we had all those 3 possibilities. Did anybody see the video that was posted to the classroom? Only a couple people. Did you watch it? Yeah? And if you hadn't watched it, you could go and check it out. It's only 5 minutes long, although there's a part 2 and a part 3 and a part 4. And so if you have more time, they're all really good. If you have any interest in mathematics at all, they're fascinating. They're so well done. If you got nothing to do in MSIP or something like that, which obviously if you're in this course, you always have something to do in MSIP. But if you're tired of doing practice questions and you just want to veg for a minute, it's super fascinating. I'll walk you through it quickly, but it gives you some neat visual representations of these things. And it talks a bit about the history, which you may or may not find interesting, but then it gets back into some of the actual math behind this stuff. And it talks about this thing that sounds really complicated. It's not that complicated, just the simple version of it at least. It sounds very important, and it is very important. And it's called the fundamental theorem of algebra. Doesn't that sound like kind of scary? The fundamental theorem of algebra, of all of algebra. Anyway, all it states is, so we just said that quadratic could have 2 solutions, or 1, or 0. But the fundamental theorem of algebra actually says that's not true. It says that if a polynomial is degree 2, it must have 2, we call them roots, but it's the same as 2 solutions. Has to. So it can't have 0. And it says if it's a degree 3 polynomial, it has to have 3 roots. And this is a proven theorem. Degree 4 will have 4 roots. And the way the theorem actually works is it says of degree n will have n roots. It's always true for every degree polynomial.
Is that because you can use imaginary?
Exactly right. So we don't learn about imaginary numbers in grade 10, but they are where if you have 0 solutions in grade 10, you actually have 2 solutions or 2 roots. They just lie in a different number system. And you don't know how to find them, so we say for the time being that they don't exist, but they actually do. And this video series explains imaginary numbers, and the unfortunate name that they were given, because they are not imaginary, they actually do absolutely exist, but they're a very strange way of thinking of numbers, and very different from how we think about them. We think about numbers in a very specific way, but that's just because that's how we've always learned about them. And I'll give you a short history. I don't want to take up too much time, but thousands of years ago, the only numbers that existed were the counting numbers, starting at 1 and going up. How many cows do you have? I have 4 cows. I have 9 cows. That's all people cared about, right? I'll trade 10 sacks of rice for 1 goat. Things like that. And then, good deal? Yes, that's a good deal. And then somebody's like, well, I want 10.5 sacks of rice. And all of a sudden, the fractions were discovered. But before that, this is a long, long, long time ago. But people didn't think fractions existed. Like, nobody knew about fractions. It would have been nice to go to school back then, wouldn't it? Math class would have been a lot easier. And in fact, 0 didn't even exist. A long time ago, people were doing some math, and there was no number 0. Didn't exist. You didn't have 0 cows. You just didn't have any cows. You had a lack of all cows. You had no cows, but you didn't have 0 cows. And then 0 was only used originally as a placeholder digit for a number like 10. And I don't think it was with our character system, so it didn't look like a 0. Didn't look like that. It was some other character. But it was just a placeholder. And then eventually, they started doing more in-depth math. And somebody's like, we need to have a number 0. And 0 was discovered. And then a long time later, for a long time, not even that long ago, even some of the mathematicians that you've heard of, this is only like 400 years, like 400 years ago, something like that. Yep. Negative numbers didn't exist, and even mathematicians, great mathematicians, didn't like negative numbers. They thought they were suspicious. So they would reorganize the math to avoid negative numbers as much as they could. But eventually they started accepting negative numbers. And just like you, when you first learned about negative numbers, you're like, what the heck are they talking about? Negative numbers? That doesn't make any sense. Back in grade 7 or 8, you're like, this is ridiculous. These numbers don't exist. You can't have -4 apples. Like, how could that be, right? It's not a thing. But now, years later, you understand negative numbers very well, and your universe of how numbers work changed. And now we're all in this universe of numbers where you have a one-dimensional number line that just goes back and forth. It can go to the positives or it can go to the negatives, and we're fine with that. What if numbers were not like that? What if a number, and I'm not talking about the XY coordinate because that's just two number lines. What if a number was two-dimensional? So a number could go this way along the integers, but could also go this way. And that's where the imaginary numbers lie. And a famous mathematician, I think it was Gauss, said, it's really too bad they're called imaginary. And they were actually called imaginary in a derogatory sense originally. They were called imaginary because when people started asking questions like, what if this was possible? What if you could take the square root of -1? The other great mathematicians at the time are like, how ridiculous, these imaginary numbers that don't even exist. They're imaginary, they're impossible. And that name stuck, which is unfortunate. Gauss wanted to call them lateral numbers, I believe. And if we had these, we would have the integer numbers going this way and lateral numbers going that way. And like, it doesn't make sense, but it is how they exist. Things that have been proven true in mathematics only work when you realize that numbers themselves are two-dimensional. But it's a whole nother world, and you did a little bit of work with I, the square root of -1 in grade 11, but we don't talk about it in grade 12. So unfortunately, we don't get into it. But if you took higher level math, you would start to get into it, and you would understand it. And eventually, it would be weird at first, but eventually you'd be like, how could you not think of numbers as two-dimensional? You would eventually get there, just like how can you not think of negative numbers?
So basically what you're saying is like every number along the number line, and they're imaginary numbers that have a number line.
Right, right. Yeah. And this video series that I was talking about, if you get to like episode 4 or 5 or so, does a pretty good job of explaining how that works. And the math isn't all that hard. A lot of it is visual. It's super fascinating. I would encourage you to check it out if you have time. Anyway, that's my quick pitch on the fundamental theorem of algebra. There's obviously more to it. Sounds very important, is very important, but it's not too crazy. Really what it says is a polynomial of degree n will have n roots. Now, everything we do, solve each of the following. X is an element of the real numbers. So we call them the real numbers when we don't include imaginary numbers and complex numbers. And those are the ones that we are trying to solve and that we are interested in. So lucky for us, we don't have to worry about it. So in our world of this course, a degree 3 polynomial equation will have up to 3 answers. It will have 1. It could have 2 solutions, although that would actually still be 3 roots, but anyway, we won't worry too much about that. Or it could have up to 3 solutions. It won't have more than that. It may only have 1, but I will say, and I'll talk about this again as we go through, if you're solving a degree 4 and you only have 3 answers, you've probably done something wrong unless like there's a reason why that turned out. As you were doing the solution, it would be obvious to you why there are not 4 answers. So that's a little thing to keep in the back of your head as you're solving these. This started out as degree 3. Why do I only have 2 answers? Where did the third one go? And it might be a mistake you made, or there might be a reason for it. Something to think about. Fundamental theorem of algebra. Super interesting. What do you notice that's different about this compared to the last unit? Like I said, a lot of what we're doing today is straight out of last unit. It says equal to 0. And in the last unit, it might have been equal to f at x. And it would have just said factor fully, and you might have graphed it. But it was a function you could graph, possibly. This is an equation you could solve because it's got a left side and a right side. And when we solve an equation, it's a little bit different from just factoring. It's got an extra step, that kind of thing. Anybody know how to start this one? By the way, we have, I kind of skipped over b squared minus 4ac as the discriminant. Sorry, we're going to talk about that. Tells us about the nature of the roots of a quadratic. In grade 10, you have different ways of solving these things. The quadratic formula works for all quadratic equations, which is really nice. Some people in grade 10 are not great at factoring, so the quadratic formula becomes their tool that they just want to use for everything. And even factorable things, they just want to use the quadratic formula. So it does work, but factoring is faster, and by now we're pretty good at factoring quadratics, so we should be fine with that. But in grade 12, we have some different ways of factoring as well. What's our tool that always works for factoring any degree polynomial? Does anybody know what it's called? Nope. That works for dividing polynomials. That's how we're going to do this one. But what's the other way that we can factor? Isaac? Factor theorem. Factor theorem, right? Like we use factor theorem, and synthetic division will work to factor anything that is factorable. So that would work in this case, but there's an easier way, and it's factor by grouping. This is a factor by grouping question. If you miss it, as I say, you can use factor theorem. But we're going to use factor by grouping. So I can factor out an x squared, and I get x plus 1. And the trick to factor by grouping is my brackets have to match. So I have to factor out a -5. If I factored out a +5, I would be left with -x minus 1, which is not the same as the other bracket. So I cannot do that. I have to factor out a -5, and I get x plus 1. Okay, and then I write out, don't forget the equals 0. And in the last unit, you might be done because this isn't factorable, right? So again, this is one of the first differences we're going to see in the last unit. You'd stop because that's not factorable. Don't write this down. You could x plus root 5, x minus root 5. That, like, you could write it that way, but typically in grade 10, we don't. But this is solving equations. So that certainly has two solutions, that bracket there. So we're going to solve them both, and I'm going to do it like this. Therefore, this is, by the way, where I'm using the zero product property. There is no operation where I'm going from this line to the next line. It's not like I added 3 to both sides, or I squared both sides, or I divided both sides by 5. I'm using a theorem or a property. So that's why we put the therefore sign in there. So it's important. Therefore, x plus 1 equals 0, or x squared minus 5 equals 0. And in this case, probably your best bet is to move the 5 over and take the square root of both sides and solve that one. And this is how I know I'm done solving an equation, because I have my x values. Yeah, thanks. Yeah.
But you could also solve this just using finding, like, doing what we did with f at x. And just finding
Yes, and we'll see an example of that next. That's what I call factor theorem, right? So you could, yes, you could, if you missed that it's a factor by grouping, you could use factor theorem. And we will use factor theorem a lot. Oh, thanks, my goodness. Yeah. All right, let's try another one. Something, I'm going to just scroll back up. You don't have to worry about this. You can get that written down and just hang out for a second and watch. Something that I make a big deal of in grade 10 is we have this thing called the zero product property. And just so you know, it only works for 0. Like, there's no 8 product property. There's this question that just comes up, and I don't know if it's the practice or the lesson that I do in grade 10 where it's like equal to 8. It's like A times B equals 8. And this is what people do. Therefore, A equals 8 or B equals 8. So two things multiply to 8. One of them must be 8. Like, what? Like 2 and 4? How does that work? I don't know. So it doesn't work for other numbers. And it's fun. You laugh. But our brain plays this weird trick on us where once in a while we see something different. And you've seen it before. You saw it in the trigonometry units where like once in a while some people are like, oh, I'll divide both sides by x. Or I'll do something, oh, this one's different. I do this a different way. No, you never do anything a different way. We're always using the zero product property. So that's how it has to work. So there's something we have to do to this before we can solve.
But for the question 8 times b equals 8, doesn't that work with all prime numbers?
No, because you could also have like fractions and stuff in there. Like you could have other solutions, so it still doesn't. You're right. If you were talking about whole numbers or integers, maybe, or like, but really, the way we conceive of it with the number 0 works differently, even from prime numbers, that kind of thing. Yeah, yeah. So how are we going to solve this? We're going to move 7x minus 6 to the other side, or move whatever you're moving, move everything to one side and set it equal to 0, so we can use the zero product property. Never be fooled. We're always going to do that. For some reason, people are like, oh, maybe this is the exception when we don't do that. No, there's no exception. We do this every time. Before we do this, I want to point out something, and I'm going to do this throughout the unit as well. It's really important. Another way you can think about this specific question, on the left side of that equation, what kind of a function is that? 2x cubed minus x squared. No? On the left.
Oh, on the left, sorry. What is it? It's not quadratic, it's the one after, I forget.
Cubic or degree 3 is fine, right? You don't need to know the word, but it's okay. Degree 3, what do they look like? And we know a bit about its end behavior. We know a little bit about what it would look like, so it might look like that. Like, I don't know exactly, but it might look something like that. Do you agree? Yes? Okay. Can't forget everything we did in the last unit. We're going to need it. What's this on the right side? It's linear. And actually, we know something about that. It's got a y-intercept of -6 and a slope of 7. So what if I drew that like this? Solving this equation is also finding these 3 points. Like it's the same thing, right? And people want to think graphing is graphing and solving equations and solving equations. They don't have anything to do with each other. They have everything to do with each other. Every time I'm solving any equation, I can think of it, and you should think of it as, what if this was a function and this was a function, and I wanted to find where they were equal? Right. So it could have the same amount of answers as like when I move the stuff over, it's just going to look like a cubic, but it's the same thing. And when I was doing this, I was finding out when this function equals 0, which is just finding x-intercepts, like we did to sketch in the previous unit. It's the same thing. And it always benefits our thinking when we think about the graphical model. People hesitate to do that because it is a little different, but it's really, really important and useful. Okay, so now let's go ahead and do this. We're going to do this kind of quickly because we don't have a ton of time, and hopefully you're very good at factoring by now. And if you're not, well, you're going to have a lot more practice, and you're going to have to get caught up. The faster you are at this, the better. You will notice that we show our work a little bit differently in this unit from how we did in the previous unit. There is no f at x. If you want to continue to use those little steps, you're going to do them off to the side. And it's just going to be for yourself. So you're going to be like f at, in this case, 1 equals 0. Therefore, x minus 1 is a factor. But I'm just going to go x minus 1. If you're going to do the synthetic division, again, you do it off to the side so that this equation flows nicely. Okay? Is going to be 2x squared plus x minus 6. So I don't want all those extra steps in here, in other words. But feel free to do them off to the side on scrap paper or something like that. And then this is where I'm going to use the discriminant. So b is 1. A is 2, C is negative 6. And so I get, like normally I wouldn't write all this out, but this is like 1 squared minus 4 times 2 times negative 6. So that's 1 squared plus 48, I believe, which is 49. So what can I conclude from this? Max? It's factorable. If this is a perfect square, I'm going to write this down in a minute, but if this is a perfect square, it's factorable. Did we talk about this in this class? Yeah, okay. So you've already seen this, and you may have already even written it down, but b squared minus 4ac, you don't have to write this down, you can if you want. Less than 0, no real solutions, no real roots. We just learned from the fundamental theorem of algebra that it has to have at least 2, but if they're not in the real number system, we're not going to worry about them. If it's negative, okay? If b squared minus 4ac is greater than or equal to 0, it has 2 real roots, so it's solvable. And if it's equals a perfect square, then it's factorable. Then factorable. Okay? And it's really useful, trust me. If you didn't believe me before when we talked about this, believe me now. X minus 1, 2x, x. I know I'm going to go through this fast. It's because we have a lot to do. So this is going to be 2, and this is going to be 3, and I believe it is minus plus. Yeah. All right, we're done. Should we move on? Why are we not done? In the last unit, we'd be done because we were asked to factor. In this case, we're solving, we're not done. I'm only going to write this one time. Usually we jump to the chase, but this means again, x minus 1 is 0, 2x minus 3 is 0, and x plus 2 is 0. I started with a cubic. Looks like I'm going to have 3 solutions. That all makes sense to me. X equals 1, x equals 3 over 2, x equals negative 2. Any questions? All right, let's keep going. What's going on here? What do you think? I've got a degree 4, so we will have up to 4 solutions. We should have 4 solutions unless something else occurs. Very nice. We can factor an x out. And Bradley? And that's a good thing because that'll make our life a lot easier in the next step. So we're going to pull out a 2x, and I get x cubed minus 27 equals 0. Now the 2, because it's equal to 0 and it's an equation, only do this if you understand it. Some people start doing this everywhere and it's wrong. I could divide both sides by 2, correct? I don't know if it's all that helpful in this case, but if I divide both sides by 2, I get this. So you can do that if you want. When you're solving an equation and one side is equal to 0, that's useful to know that I could multiply through by negative 1, I could divide by 2, I could multiply by 2, like I could do all these things. That doesn't change the equation. Isaac? Difference of? Cubes. It is a difference of cubes. Again, you could use factor theorem for this, but that would be like, oh my gosh, what in the world are you doing? Why would you do that, right? So it's going to be x minus 3. And forgive me for not giving everybody a chance to try all of these. We don't have enough time, I don't think. So I'm going to kind of go through and do a lot of the factoring myself. This should be x squared plus 3x plus 9 equals 0. What do we do next?
Check if the quadratic is happy.
I love it. B squared minus 4ac. So 3 squared, which is 9, minus 4 times 1. Again, normally I wouldn't write all this out. 9 minus 27. Sorry, 46. I'm getting ahead of myself. 36. I'm getting ahead of myself, which is negative 27. So not solvable. No solutions here. So for this part, I'm going to say that b squared minus 4ac less than 0, therefore no solutions. But I have these other two, x equals 0 and x equals 3. It was degree 4. I should have had 4 solutions. 1, 2, the other 2 would be there, which would be imaginary solutions. They do exist, but we don't know how to find them. We're not going to worry about them. Yes?
Wait, if it's just like finding where linear and another graph meet, or another like line meet, couldn't like a linear have like a low enough slope that it just completely misses all of the other line? Like going back to the graph.
Whoops. Hold on. Like that? Yep.
Yeah, so couldn't there be less than?
They'll always cross once.
Yeah, but couldn't there be less than the degree? Even if they cross once, that's fine.
Real solutions. There will be complex solutions. There will be imaginary solutions. Always.
But it's fine to have only one.
Yeah. Like we only have 2 real answers here because that's the number system we're using. Yep. We don't have time for that, unfortunately. Remember, anything else to say about that before we move on? Okay, so I want you to say that this is not solvable. Okay, whenever you get a quadratic, you have to show me. You could try the quadratic formula on this, and you'd get a negative, or you can just check it and say b squared minus 4ac is less than 0. I will allow you to do that, so you don't have to write out the whole quadratic formula. But you have to say some reason why this isn't factored. If you just stop there and wrote out your 2 answers, you're losing a mark because I'm like, what about this? Okay? Okay. Graphing, when we have imaginary numbers, becomes different. So it's not going to be quite the same visualization that we can do in the real number system. Our graphs on the xy plane are for the real number system. So those visualizations will only work for those solutions. Does that make sense? This one's easy. I don't know why this one's here. It's already factored. So 3x minus 1 equals negative 10. X minus 2 equals negative 10. And is this right? X plus 4 equals negative 10. You know that negative 10 product property? What do we have? What am I doing wrong? What do we have to do here? Yeah. And here's what some people do. They just move the 10 over and then try to solve like that. That's not going to work either. What do I have to do to solve this whole thing? We got to expand that monster. Expand, simplify, move everything to one side. We haven't done a lot of this. I'm going to do it quickly, and I'm not going to leave you to do it because it's going to take too long, but I would do these 2 first because I could do them in one step. So I'm going to leave the 3x minus 1, but you could do them in any order, of course. Make sure you're still multiplying. X squared, 4x minus 2x is 2x minus 8 equals negative 10. And then, just watch for a second. I would go this, and this, and this, and that, and that, and that, and get 6 terms. But I also know that the first term, is going to be 3x times x squared, which is 3x cubed. And this is what I know. I know the x squared term will be this times this and that times that only. So if you want to save yourself a step, you can do that in your head. If you can't do that in your head, then do it in 2 steps. But it's going to be 6x squared minus 1x squared. So this is going to be plus 5x squared. And if you didn't totally follow that, just expand it the way that you're used to doing it. And you can just trust me that the answer here is going to be correct. To get my x term, it's 3x times negative 8 and negative 1 times 2. So negative 24 minus 2. And then negative 1 times negative 8 is plus 8 plus 10 equals 0. And really, I probably could have added those together to save myself rewriting it, that whole thing there as well, right? That would have been pretty easy to do. And I've already checked. 1 works. Let's see. Look, 18 plus 3 is 21. Plus 5 is 26 minus 26. So if I put 1s in for all those, it's going to work. So that means x minus 1 is a factor. And again, I'm going to do this quickly, but you might use synthetic division off to the side. But notice how I'm not doing the f at negative or f at 1 equals 0, therefore x minus 1. You no longer have to do that. If you want to, do it on the side. 3x squared plus 8x minus 18 b squared minus 4ac, oh dear, is 8 squared, so 64, plus 4 times 3 times 18, 280. Not a perfect square. Therefore, we're going to use a quadratic formula. Now be careful because sometimes people miss one of their solutions here. So therefore, I've got x equals 1 from that first bracket. And I've got x equals negative 8 plus minus square root of 8 squared minus 4 times 3 times negative 18. You have to write this out, yes. You don't have to write out the formula. You didn't write it out the first time, you just solved it. So you got to show the substitution. Minus 8 plus or minus 280. And then at this point, if you're asked for exact answers, you would have to reduce that. So, oh boy, 280 divided by 4, you get 70. So that's probably the best that we can do. So this is 4 times 70, which is negative 8 plus or minus 2 root 70 over 6. And I can simplify this further. Negative 4 plus or minus root 70 over 3. And again, depending on the instructions, if you're asked for exact answers, I've got them. I've got 3. It was cubic, and I have 3 solutions. That's all makes sense. If you're asked rounded to 2 decimal places, or 1 or 3 or whatever it is, then you show that. Any questions? All right, I believe we have one more example to try. And then one more little thing to talk about, otherwise we are pretty much done. So how would you approach this question? What would be our first step?
I would just start plugging in numbers to see or use factors.
Yeah, factor theorem. So start with, and in other words, very good. I love it. Start plugging in numbers, looking for 0, a remainder of 0. What would you try first?
1,
And then?
-1,
And then?
7,
Okay, good. And then?
-7.
What if none of those worked?
Fraction.
What if none of those worked? Not necessarily. There can actually be a solution. Zero won't work unless I have a common factor of x, and even then it's not going to be all that helpful. What if none of those worked? Thankfully, one of them does work. Let's do that first. -7 worked, so it would have been the fourth one you would have tried. We didn't have to try 2, 3, 4, 5, 6 because of the 7 there. Hopefully you remember that, because that would have been a lot of extra work. You would have think of all the things you would have tried before you got to -7. You only really had to try, and 1 and -1 you can see clearly aren't going to work. So you try 7, doesn't work, -7 does. Okay, and then our result is 6x squared. I think plus or minus x, yep, that's right, minus x minus 1. B squared minus 4ac is 1 plus 4 times 6, so it's going to be 25. So this is factorable. It's got to be 3 and 2. And it's going to be 1 and 1, and then it's going to be negative and positive equals 0. Therefore, x equals -7, -1/3, and 1/2. Okay, there was a reason why I was asking that question in the beginning, though. What if -7 didn't work? What are the other two solutions? They're fractions. Remainder theorem and factor theorem tells us if I plug these fractions in, I would get 0. So if 7 didn't work, -7, you got to start trying fractions. That's a little bit tricky, but go ahead.
You have to check the multiples of the first coefficient.
Very nice. So it has something to do with this coefficient here. I don't think you need to write this down. And you won't have to do this. I'm not going to make you do this, but I want to point it out in case it came up next year or something for you. Yeah. Not all factors must be of the form m over n. Sorry, all factors must be of this form. So we already know the ones for m, but what about the ones for n? Think of nx minus m as a root. Think of this, where the 3 and the 2 are factors of the 6, and the 7 and the 1 and the -1 are factors of the 7. So the full list is actually includes the 7 and the 6. So I've got 1 and 7, and I've got 1, 2, 3, and 6. Okay, so my possible factors are this list over this list. Plus minus 1 over 1. Plus minus 7 over 1. Those are the ones we've already seen. Plus minus 1 over 2 plus minus 1 over 3 plus minus 1 over 6. Our list all of a sudden got bigger. 7 over 2 plus minus 7 over 3 plus minus 7 over 6. That would actually be the full list you could try. And if none of those worked, then it's not factorable. I'm not going to make you do that though, so don't worry. You just have to check integer solutions. But just so you know, that's where the other ones would be if you had to check them with factor theorem. Very last thing, and this is again just a visual. We kind of already talked about it, so I won't go too much into it. But what if you were given some question like this and you were told, use the graph to visualize what's happening here? Well, I can see that this is degree 3. So the green one is f at x because it's degree 3. It's a cubic graph. And this is degree 2. So this is the blue one, g at x. So if I was going to solve f at x equals g at x, as we talked about before, I would be finding those points of intersection. Always a good way of thinking about it. The other one was a cubic and a linear. This is a cubic and a quadratic. And it sounds difficult because in grade 10 you learn how to solve a linear system and it's fairly complex. And now all of a sudden we can solve all kinds of systems. But it's actually not that hard. We just throw everything on one side and solve by factoring. It's not actually that bad.